Alright, let's talk about group 4 metals. Those particular metals correspond to the alkaline earth metals other than beryllium, and even lithium gets incorporated in here because of its similar chemistry compared to the rest of the alkaline earth metals. And pretty much what happens is that at this point you have removed the group 1 ions by adding HCl. Then you added acidic H2S and remove the group 2 ions, at which point you raise the pH either, or you added ammonium sulfide in basic solution to precipitate the group 3 ions. Now magnesium, calcium, strontium, after all of those steps, still remain in solution. So the way you get them out is by adding carbonate. Now it's very important to point out that most things are insoluble with carbonate, so it is very important that you do remove the other ions first before you add carbonate, because if you do have any group 1, group 2 or group 3 ions in addition to the group 4, if you decide to add carbonate at that point, you will precipitate everything, groups 1 through 4, and that basically doesn't help you whatsoever, because you basically still have the mixture that you started with. So you have to remove the other 3 groups prior to adding carbonate. Because unlike the alkaline metals, unlike the alkaline earth metals, most of the alkaline metals, sodium, potassium, rubidium, don't precipitate with carbonate, and that's the reason why we call those particular metals the soluble metals. Alright, so here it is. If we look at the carbonates, we can see that each one of them have KSP values, and they're not necessarily very large. In fact, for lithium, that's kind of borderline to the point where even I include lithium plus as a soluble cation. But by the time you get to calcium, the values get kind of small enough that yes, you could end up generating precipitate. So let's take a look at that. Let's look at lithium carbonate, for instance. Okay, so with that low value, or that technically higher value of KSP. If we calculate what's going on for lithium carbonate, and since the fact is that the KSP is less than 1, we could use your typical ice table with excess, and we could have an initial concentration of 0, basically just add the salt and see how soluble it becomes. The change in concentration would be plus 2x for lithium and plus x for carbonate. Alright, so you have your equilibrium concentrations now, 2x and x. So for your KSP, you have lithium squared times carbonate to the first power, which gives you overall the value of the KSP, 8.15 times 10 to the negative 4, equal to 4 times x to the third power. So if you divide both sides by 4 and take the cubic root, you're going to find out that the concentration of x is 0.059 molar, which means that for lithium, that will be twice the amount, so 0.118 molar, and the carbonate concentration will be 0.059 molar. So these are actually concentrations that are not atypical. In fact, they are relatively high for most of the chemistry that we tend to do. So pretty much lithium carbonate, for the typical concentrations that we use in chemistry labs, can be considered as soluble, because you don't need to go much higher than 0.1 to do most of the chemistry. But that being said, if the concentrations go above 0.1 for both of these things, then you're very likely to end up with a precipitate. Alright, so that's one thing to be said about the group 5, the group 4 metals. And you could perform a similar characteristic calculation for calcium, strontium, and so on and so forth, and you'll find out that yes, the concentrations are lower than that. Now the group 5 elements are, simply stated, the rest of the alkali metals: sodium, potassium, rubidium, cesium, and francium. And these guys are basically always soluble. So by the time you have added your HCl, follow that up by adding acidic H2S, follow that up by adding basic ammonium sulfide, and ending up by adding sodium carbonate, you have basically removed everything except for the alkaline metals. These are the only things that will still remain in solution, and this will be the last type of ions that you expect to have left over in your original solution. So just to give an idea, in the future I'll probably be using beyond labs to show you this even in more detail. But to give you an idea of the process, here we have a copper 2+ solution, which if you add ammonia, dilute ammonia to increase the pH, initially you can form a solid, a precipitate solid. But if you continue adding more ammonia, kind of make it concentrated, you get that that insoluble solid to ultimately go back in solution, because now you form a complex ion. So it's simply by keeping the concentration of ammonia in check, you could select for an insoluble copper complex or a soluble one. And the way you basically gauge how much ammonia you have present is by changing the pH. At lower pH, you're going to have lower concentration of NH3. At higher pH, you're going to have higher concentration of NH3. So just by tinkering with the pH, you can select precipitation over dissolution. And then for lead, kind of a similar idea. You have lead hydroxide, you have lead iodide. So if you add, if you raise the pH for lead, you're going to form a precipitate. If you add iodide to a lead solution, you're going to form this yellow precipitate. And technically speaking, what you do with the precipitates is you centrifuge them. You add them to a centrifuge, and technically what the centrifuge does is it rotates, and you can kind of see you have this circular pattern right here. You add your solution in these tubes, and the centrifuge literally rotates the tubes at really high speed. And what ends up happening is that by centrifugal force, the solid materials get pushed towards the center of the rotation, which in this case is the bottom of the tubes. And by doing that, you ultimately collect the solids as pellets at the very bottom of the tubes. And simply what you end up doing is decanting away the supernatant liquid from the solid. You basically tilt it. You might even need to use a steering rod to keep any solids from exiting the tube. But that's literally how we separate the solution mixture from the precipitate. And this is also the way by which we remove the group 1 cations from the group 2 cations, etc., etc. So it's a kind of nice little procedure that I kind of want to give you some proper context as to how the whole thing gets done. Alright, so with that being said, we have finished the mixed equilibria chapter. It's a little complex in the sense that we are adding multiple types of equilibria together, and it does require that you do remember the definitions of KSP in terms of writing the equation, the definitions of KF in terms of writing the equation, and the definitions of KA and maybe even KB in terms of writing the equations, at which point you have to apply a little Hess's law cycle to get a few things to cancel out and yield the final desired equation for which you're actually doing equilibrium calculations. Okay, so we'll stop this video right here, and I will see you in the next series, which is thermodynamics.